Imagine this snowball is like an atom. Adding more snow makes the atom grow bigger, but it also makes it harder to keep together. The same thing happens when nature tries to make bigger and bigger atoms. Eventually, one more handful of snow will be too much, and it'll break apart. Scientists have known this for a while about atoms like uranium. Sometimes they just have to split. Today's nuclear research began in 1896 with French scientist Henri Becquerel, who discovered an intense radiation coming from the element of uranium that would pass straight through solid materials. Becquerel's student Marie Curie and her husband Pierre continued in this new field of research and coined the term radioactivity. In 1932, James Chadwick discovered the subatomic particle we call the neutron. This important discovery was the backbone of the research of scientists Otto Hahn, Fritz Strassmann, Lise Meitner, and Otto Frisch, who, in 1939, discovered the process of nuclear fission. During the Second World War, nuclear research was pushed forward in the United States, achieving the first sustained nuclear chain reaction in 1942. Canada followed close behind with the second nuclear chain reaction in 1944. This and other research done in Canada was instrumental in further developing nuclear science research around the world. To understand nuclear fission, we have to think small, like really small. Atoms are the fundamental building blocks of the universe and make up all matter. When you get down to it, atoms are made up of a nucleus in the center, with tiny particles called electrons buzzing around it. Nuclear energy comes from an atom's nucleus. Get it? In our model of the atom, the nucleus is made up of protons and neutrons. For example, the helium atom is made up of 2 protons and 2 neutrons. Its atomic weight is 4. 1, 2, 3, 4. So this atom is called helium-4. This uranium nucleus is much larger, and it contains 92 protons and 143 neutrons, giving it an atomic weight of 235. This time, adding another neutron to this atom makes an extremely unstable isotope, which will almost immediately break apart into 2 smaller atoms. 3 extra neutrons are released along with about 200 mega-electron volts of energy. The extra neutrons in this reaction go on to collide with more uranium atoms, which in turn create more neutrons and more energy. This is called a nuclear chain reaction. Nuclear reactions can be controlled in a nuclear power plant facility. At Chalk River Nuclear Laboratories, research reactors like this historic NRX reactor are used to study many present and future applications of nuclear energy.
Nuclear fission is used in nuclear medicine for imaging and diagnostic and treatment, as well as in food irradiation and sterilization. So, for example, it's used to kill bacteria and other pathogens and extend the life of various foods. It's also used in sterilization of medical instruments for surgery, for example, or syringes, needles, and so on. We're also using it for safety-related applications and like border security, anti-terrorism, and so on. So those are just a few examples.
Inside the Chalk River Nuclear Laboratories, there is so much more than meets the eye. Biological research facilities are testing new treatments for heart disease. Nuclear safety tests are done each day, and new developments in fuel recycling are ensuring that the future of nuclear energy is safe and clean for everyone.